An insulated container of gas has two chambers separated by an insulating partition. The words insulated and insulating suggest that the process here has to be adiabatic. Correct? The process, whatever process that is, that has to be adiabatic. Q cannot be non-zero. Okay? One of the chambers has volume V1 and contains ideal gas at pressure P1 and temperature T1. The other chamber has volume V2 and contains ideal gas at pressure P2 and temperature T2. If the partition is removed without doing any work on the gas, the final equilibrium temperature of the gas in the container will be T1 T2 into bracket P1 V1 plus V2 V2 upon P1 V1 T2 plus P2 V2 T1, P1 V1 T1 plus P2 V2 T2 upon P1 V1 plus P2 V2, P1 V1 T2 plus P2 V2 T1 upon P1 V1 plus P2 V2, and T1 T2 P1 V1 plus P2 V2 upon P1 V1 T1 plus P2 V2 T2. Dimensionally all of the options are giving us temperature, so that cannot be used. Okay, fine. Let's see if we can draw the figure and see what we get. Okay, so suppose this is that partition. This is V1, this is V2, this is T1, this is T2, and let's say this is P1 and this is P2. Okay. Now look, if we consider the container as our system, very important. Okay, if we consider container as our system, then Q is 0 and W is also 0. Okay, do you realize that? Why is W 0? W is 0 because delta V is 0 for entire system. Had we considered the volume V1, then that would have been some mass flow out, some mass flow in after removal of the partition, but we are not interested in that. Okay, so the whole container is our system. Q is 0, that is given in the problem itself, adiabatic. And why is W 0? Because delta V is equal to 0, because our volume, our system's initial volume is V1 plus V2 and our system's final volume is also V1 plus V2. Is it clear?
Yes, sir.
Now these two statements are important because if Q is 0 and W is 0, okay, Q is 0 and W is 0, what does it mean? Look, Q minus W, which is delta U, that is also 0. First law. Okay? Delta U is also 0 according to first law. Now look here. Is it given how many moles of ideal gas are there? Okay, it's not given. So let us suppose that there are N1 moles here and N2 moles here. Okay. And let's now try to consider the balance of the internal energy. Okay. So U1 plus U2 is equal to U. Can write it. So U1 plus U2 basically means initial internal energy of the system. And this is the final internal energy of the system. Okay. This is the final internal energy of the system. Okay. Now considering U as of, look, there is no state change here. There is no phase change happening here. Assuming that, I can write, and it's the same ideal gas, right? It is the same ideal gas, so same specific heat. Okay, so what can I say? same specific heat. So let us consider number of moles as N1 for this. So N1 CT1, C is the specific heat, plus N2 CT2 is equal to N1 plus N2 C specific heat, and let T be the final temperature, or T final. Okay, then we can remove or cancel these things, and therefore T final would be N1 T1 plus N2 T2 upon N1 plus N2. Pretty much like the section formula. Not exactly analogous to section formula, but we can say weighted average of temperatures. Yeah, that's a better framing, because for section formula it is N2 T1 plus N1 T2, right? Weighted average of temperatures. Okay. Now, can we bring in ideal gas equation? Yes, of course we can bring the ideal gas equation, which tells us that PV equals nRT. So what will be NT? PV by R. Okay. So N1 T1 will be P1 V1 by R1. This will be P2 V2 by R. Sorry, no, not R1. R only. Sorry. PV by R. Yeah. P2 V2 by R, and what will be N1? N1 will be P1 V1 by RT1. N2 will similarly be P2 V2 by RT2. Okay, P1 V1 by RT1 plus P2 V2 by RT2. Correct. Now we can eliminate R. And then what we can do in the denominator is P1 V1 T2 plus P2 V2 T1 upon T1 T2. So that T1 T2 will sit in the numerator. So P1 V1 plus P2 V2 in brackets. So these are not involved. And in the denominator is P1 V1 T2. So this is also not there. So correct option is A. Raise your hands if you understand the problem. See, the solution will depend on what you take as a system, because we do not consider open systems. Okay, well, we can consider them if we want, but suppose we don't consider that, then definitely we need to take our entire container as our system. That will make our analysis simpler, and that will also take us to the quantity that we want to determine.